Euler-Lagrange equations for n variables. Recall that we have for one-dimensional or for one function y of x the following Euler-Lagrange equation, that if we solve this equation and find y of x, that will give us stationary functional s, and f is some other function or generating function for which this functional will be minimized. The beauty of Euler-Lagrange approach is that we can expand this method to to many variables or many unknown functions y, 1 of x, and all the way to arbitrary y n of x. And we do that by introducing a new mother function, and this mother function, by the way, we will later see is known as Lagrangian, which will be defined in terms of all these functions that we will seek to find and their slopes, well, and as well as the independent variable x. So let's imagine that this is how our new mother function will look like. So the question that we want to ask is, what equations will give stationary functional s? So what equations will give stationary functional s? In analogy with the case of only one function y of x, we require that these functional derivatives ds, dy1, ds, dy2, and so forth and so on will be equal to 0. Now, once again, and again proceeding very much like we did it in the one-dimensional case, let us write variations for each individual function in terms of a number alpha 1 and eta 1 of x, where eta 1 is arbitrary function which passes through the bounds. So it vanishes at x1, and eta x2 goes to 0. Okay, so that's the requirement that we will apply. And so for all of these different functions, we will use a similar definition. Of course, in each particular case, we are dealing with different function eta, all the way to the variation for function y sub n. Okay? So, just like we did for the one-dimensional case, we can show that these functional derivatives here now can be written in terms of partial derivatives that will be written as partial derivatives of s with respect to alpha 1, alpha 2, and so forth, all the way to alpha sub n. So in fact, these two requirements become the same. So this is the same. Now, if we proceed and we find each of these partial derivatives, we discover that we obtain a result that looks very much similar to what we already saw. So namely, for the first equation here will give us partial derivative of f with respect to y1 minus full derivative with respect to x of partial derivative of f with respect to y1 prime. Okay. And so forth and so on. So the second one, the second requirement of partial derivative of s with respect to alpha sub 2 will give us the second equation, and all the way to the last one, which will give us the partial derivative of f with respect to y sub n minus full derivative with respect to x of partial derivative of f with respect to the slope of y sub n. So what we obtain is the system of n ordinary differential equations,
Euler-Lagrange equations,
that will guarantee that the functional s is stationary.
As we shall see, the system of n Euler-Lagrange equations will become important in mechanics when we need to describe motion with more than one degree of freedom.